Hello. This video is going to be on domain and range, which is the second half of section 2. But before I do that, I wanted to talk about something called the vertical line test, which is the graphical way for you to decide if you have a function. So we're going to go back to functions real quick. So just, again, good note taking. Always title it with what we're talking about. So this is functions and the vertical line test. And a lot of times the vertical line test can be abbreviated as VLT. So if you want to be one of the people that like to abbreviate that, be my guest. And what it means is you imagine, so you don't actually draw anything, you just imagine vertical lines slicing through the graph. And we're talking perfectly vertical. So you're imagining perfectly vertical lines slicing through the graph. If any vertical line, so any of them, doesn't matter if it's only one, if any vertical line crosses the graph more than once, the graph does not represent a function. And we'll talk about how this ties into the definition of a function from the previous video, okay, as we do the examples. So let's make a little sketch here. We have our x-axis and our y-axis. And let's say the graph looks like this, okay? So decreases as it comes in from the left, then turns back upward and increases as we go to the right. Remember, we're going to imagine vertical lines. Now, for the sake of the video, I'm going to draw in some dotted lines just to fill in what we should be picturing. So we're picturing vertical lines just everywhere through the graph. Do any of these vertical lines cross that graph more than one time? No, they won't. And so because they won't, we can say, yeah, this passes the vertical line test. This is a function, okay? So it's a function and it passes the vertical line test, okay? What does that have to do with our previous video? Well, remember the concept that every input is only allowed one output? So by drawing these vertical lines, I'm saying, okay, does this input give me one output? Yeah, it does. Does this input give me one output? Sure, it does. Does this input give me one output? Absolutely. And see, these vertical lines are being drawn because I'm going to a particular x value, and then I'm seeing if it gets to the graph one time. So we are still using the basic definition of a function that every input is only allowed one output. And the vertical line test is kind of a shortcut way for us to figure that out, okay? It's more of a visual way for us to figure that out. Let's look at another quick example before we move on to domain and range. Here's our x-axis and our y-axis. Let's say the graph is situated this way this time. And I'm going to do the same thing, okay? Imagine these vertical lines, okay, going through the graph. Well, let's take one of them, for example, okay? If I take this vertical line, I cross the graph here, and I cross the graph here. I failed the vertical line test because this particular input has two possible points on the graph. That's not allowed. And so this is not a function. Or in other words, it fails the vertical line test. And again, going back to the basic definition, the reason it fails is because we can find inputs that have more than one output, and that is not the definition of a function. So this is kind of a shortcut way to determine if you have a function graphically. So now we're going to talk about domain and range. So this is still section 2, still important to label things, but now we're talking about domain and range. So before we can talk about them, we have to define them, okay? There's always going to be vocabulary that has to be kind of mastered first. You want to make sure you're using the correct terminology. So let's define what we mean when we say domain. The domain is the set of all input values. So what is allowed to be plugged into the function? It is different from just saying input because you're actually talking about listing values. You're talking about all the values that are allowed. Whereas input, if you remember it from the previous videos, input is really discussing the variable, okay? What is the thing that is changing, okay? It's more of a description, okay? And the domain is talking about actual values, okay? The list of all values. So a shortcut question for yourself when asking about domain is, what values am I allowed to plug in? Okay, because you're talking about input, so plugging in. Another key phrase here is allowed, right? Because domain is often connected to a practical example, a real life situation. There might be situations where certain numbers just don't make sense. They would not be allowed, and so they would not be part of your domain. So you have to also consider what situation you're in. Is it a generic example where you could plug in really any number? Or will there be restrictions on the numbers that you're allowed to plug in? And we'll talk about that as we do some examples. Now, moving over to range. If domain is the set of all inputs, well, guess what range is? Range is the set of all. I'm going to use the word corresponding here, and I'll explain why. Corresponding output values. The reason why I'm using the word corresponding is, remember, you're not going to get an output if you don't have an input that will result in that. So I use the word corresponding here because you have to have an input that will give you that value. Okay, so again, it's kind of like what's allowed. What are you actually going to get out? So the question that you should ask yourself is, what am I allowed to get as a result? And these are hand in hand because we know that to define our range, we need to know our domain. Okay, so they do go together because they're tied to input and output. Okay. Now, there is notation that goes along with domain and range. It's called intervals. Okay, we want to know what intervals are going to be allowed. So I'm going to show you a little bit of interval notation before we get into the concrete examples. So let's take a look at interval notation. You might remember this from previous courses that you've taken. If you don't worry about it. So let's do a quick number line here. Let's say we have -1, 0, 1, 2, 3, okay? Let's say we have an open circle at -1 and an arrow that is pointing to the positive side, okay, to the right side. There is a hole here at -1. I would not be able to stand here at -1. So that means -1 is not included. I can get really, really close to -1. I can be at -0.99999, But as soon as I get to -1, I would fall through this hole, okay? I can't stand there. And so if you can't stand at that value, you use an open parenthesis to show that there is a hole there, okay? So that is not included. So this would be shown as -1, comma, infinity, because I can keep moving to the right, okay? So I can keep getting more and more and more positive, okay? Infinity, by the way, will never, will always have a round bracket, okay? So just keep that in mind, right? So let's think about this. Why do we have a round bracket here? We can't, quote unquote, stand at -1. So we use round parentheses. That's the purpose of the round parentheses, to say that it's not included in the interval, okay? If we were going to use less than greater than notation, which more students get incorrect, so I'm going to steer you more towards interval notation. But if you wanted to use inequality notation, you would be saying that this is all x values greater than -1. Okay? But again, I find this to be a little bit easier because you're describing the interval very specifically. Now let's do another example on a number line. Let's say we have -1, 0, 1, 2, 3, 4. We have a solid dot at 4, and this time the arrow is coming to the negative side or to the left. The solid dot means I can stand there, okay? I can stand at 4. 4 is included in the interval. But order does matter. We still walk from left to right. We read from left to right. We move graphically from left to right. Everything's going to be read from left to right. Because there's an arrow here, I'm going to keep coming in from -infinity. There's no boundary here. So I'm coming in from -infinity, and I'm coming up to 4, and I can stop at 4. So see the square bracket this time. The square bracket is used because we can, quote unquote, stand at 4. So we use a square bracket. That's how we're going to show that in our notation. If you wanted to discuss this in, again, inequality form using less than and greater than, you would say this is all x less than or equal to 4. You're using an equal to now because you can stand there, okay? So it could actually equal 4. Again, I find that more students make mistakes with the less than greater than notation, so this usually is a little bit easier because you're more descriptive of the interval. So these are two examples of what is called interval notation. And this is what we're going to use to describe domain and range, okay? So let's take a look at some examples. We're going to do them graphically first. These are directly out of your textbook, okay? So I'm just going to zoom in to this one first. Okay. One thing I didn't like is they're not labeled. The axes aren't labeled. So we have our x-axis and our y-axis. The way to determine domain, remember domain is the set of input values, is that I have to walk along the input axis, okay, the horizontal axis. As I walk along the input axis, I don't have any graph over here. My graph doesn't start until I hit -5. That's when my graph starts on the x-axis. So when I go to list my domain, which I'm just going to label with D for domain, I have a solid dot here, which means I could stand on the graph here. So that means I have a square bracket at -5. That is the first value where I could stand on the graph. Okay, input value where I could stand on the graph. Then I continue walking. Yes, I still have graph. I can see graph. I can see graph. When do I stop seeing graph? I stop seeing graph when x equals 4. Okay? And again, it's a solid dot. That means I can stand at 4. So this goes up to 4. And again, I have a square bracket because I can stand there. So this graph exists for all x values from -5 to 4 inclusive. Okay, I can stand at -5 and I can stand at 4. Okay. Now let's talk about our range. Our range is the y values where the graph exists. Okay, what outputs am I allowed to get? You can do one of two things here. If you feel comfortable reading vertically, okay, then you don't have to change this picture at all. Okay, you're just going to walk from bottom to top. You're going to walk vertically. If you're not comfortable doing that, you can physically turn the graph so that you're going from small to big, just like when you do domain. Okay, that's a little trick that you can use. Remember, though, that you're looking at y values this time because you're walking along the y-axis when you do this. Okay, so just so we can read it, I'm going to do this vertically. But remember, you can turn it around if that makes more sense. As I walk up the y-axis, I don't have any graph down here. I don't start to see graph until I hit -1.5. That's the y value that I would be at right here. And I have a solid dot. So when I write my range, which I'm going to show with an R for range, I can stand at that point. So it starts at -1.5. And then I continue to see graph. There's no issues. I continue to see graph until I hit this point, and then I don't see graph anymore. So this y value is 3.4. So I stop seeing graph when the y value is 3.4, and I can stand there. There's a solid dot there. So I'm going to put a square bracket. Notice that they don't have to be represented by the same ordered pair. My domain had to do with these two endpoints, but my range had to do with these points. Okay, so it's all a matter of where do I enter the screen, where do I exit the screen. It's very similar to cropping a photo. Okay, so think about when you Photoshop something, when you crop a photo for posting on social media, it's very similar to that. Okay, you just have to determine where that picture exists. Let's look at another example. Okay, now this graph has arrows on either end, and if it doesn't in your picture, make sure you put them in because they're meant to be there. Okay, this pattern continues in this direction and that direction. Okay, if the arrows are there and I walk in from the left, because that's what I have to do for domain, I have to walk the x-axis, I'll always have graph because this is going to keep that pattern going in this direction. So that means that my domain is coming in from -infinity because that arrow is telling me this pattern keeps going. There's never going to be an endpoint. And then as I keep walking along the x-axis, will I ever stop seeing the graph? Well, I have an arrow here too. So that means that this pattern is going to keep going. So the graph will never stop. This is going from -infinity to +infinity. The reason that infinities will never have a square bracket is because infinity is not a number. It's not something you can stand on. So infinity is never going to have a square bracket. Now let's talk about the range here. Remember, range, you can physically turn the paper if you want, but you're changing the axis that you're walking on. You're now walking up the y-axis. Order does matter. You have to go small to large, okay? So always make sure you're thinking about that orientation. So as I walk up the y-axis, there is no graph down here. I don't start to see graph until -1. And then you can see I can stand on all of these little dips that are here. I could stand on them. So I am putting a square bracket at -1 because I can stand on the graph. And then where does the graph stop existing? I still see graph all the way through here until I hit +1. And again, there's no holes here. I can stand on the graph. So this is going to take me to +1 with another square bracket because I can stand at those endpoints. Okay, let's try it again. Here's another example. We're going to do domain and range. This one also has arrows on the end. So if I was going to walk in from the left, there's an arrow here, which implies that this would keep on going in this direction. So even though it's not physically drawn, I would have graph back here. So this domain is coming from -infinity, and I can pass through, and there's an arrow on this end, so it's going out to +infinity. So again, this domain will be all real numbers. That is another shorthand way to say this. So if you wanted to actually write all real numbers, that would also be true. Now let's do range. We got to walk in from the bottom, okay, because we're walking along the y-axis. There's no graph until I get to this y value, which is 5, and I can stand there. That's a point. So I have a hard bracket at 5. And then I continue walking, and this time the arrows are going to continue with me. So there's not going to be a place that I stop seeing graph. So this is going to come out to infinity. And remember, infinity will always have a round bracket because you can't stand at infinity. So this is how you do domain and range graphically. Now, we can also talk about domain and range from a real situation and from a formula. So now let's talk about it from a real situation. Let's say that the situation is you throw a ball in the air and see how high it goes in feet after X seconds. Now, got to remember something from our previous videos. The first thing that you should do here is to identify your input and identify your output. They're kind of giving you a little bit of a help because they're saying X seconds, and X is typically input. So my input here is going to be the seconds. And that should make sense because time is independent, okay? And that means that my output is the height, which is being measured in feet. This is going to be important because you have to acknowledge that you're talking about seconds when you're thinking about domain, okay? So now I'm actually going to give you a little bit more information here. I'm going to give it to you in the form of a graph. Here's our seconds, and here is our height in feet. Remember, good labels when you're doing a graph. Let's say the graph looks like this. We have 0, 3, we have 1, 19, and we have 2.1, 0. I want to know domain and range, okay, of this situation. Now, there's a very important reason why this picture is cut off, because the domain and the range purposely cut this off. Will there be any such thing as negative seconds? No, that doesn't make any sense, okay? Negative seconds don't exist. Will there be any such thing as negative feet in the air? No, that doesn't exist unless it's going to go underground. And so even though the formula for this might actually give you a full graph, you have to be the one to acknowledge that, wait a minute, this is a real life situation. There's going to be a restriction on how many seconds, and there's going to be a restriction on the height. So now let's put this all together. I'm going to talk about domain and range from this situation. My domain, there's no such thing as negative seconds. I wouldn't start the clock until 0 seconds. So I have a hard bracket, a square bracket at 0. When will this object hit the ground? Okay, the ball hits the ground here, because remember, this is seconds and this is feet. So after 2.1 seconds, it's back on the ground. It's 0 feet in the air. So it took 2.1 seconds for that to occur. Start time and stop time, okay? Real life situation for a domain. What about the range? Well, remember, range is corresponding to output, which is feet. We said that this is not going to go underground, okay? So I'm not going to see the ball unless I'm at 0 feet, okay? That's the ground. So 0 feet is as low as it could go. And then how high does it go? Well, if I keep walking, the highest height is 19. So it's going up to 19 feet. This is what we would call practical domain and range, because it is related to a practical situation or a real life situation where you have to consider what makes sense. Last but not least, we're going to talk about domain from a formula. So this is now domain from a formula. The good news is that we're not doing range from a formula, okay? We're only going to do domain. Let's say we had f of x equals 3 over x minus 5. This is where you have to be a little bit more sophisticated with your knowledge of fractions, okay? Because this is a fraction, 3 over x minus 5. 3 is the numerator, x minus 5 is the denominator. You have to know that you're never allowed to divide by 0. 0 is never allowed in the denominator of a fraction. That's an important fact, because if 0 is not allowed to be in the denominator, when you divide by 0, it's undefined, okay? That means that we need to restrict anything that would make this 0. So we're saying x minus 5 can't ever equal 0. Well, there is a value that makes that 0, okay? If x was 5, this does happen, okay? 5 minus 5 is 0. So I'm going to have to figure out what is going to be the bad case, okay? What's not allowed. So this tells me that x can't be 5 then. And then all you have to say for the domain is that x can't equal 5. And it's as simple as that. X could be anything else, but you do have a restriction here, okay, that x cannot be 5, or it would make this whole thing undefined. So I hope this makes sense. Again, if you have any questions, please don't hesitate to ask, and I will see you in the next video.